Swayam Prabha. Digital India. Educated India.
Welcome to 21st lecture of video course on tribology. Today's topic is solution of Reynolds equation. I can use a word also solutions, because we do not use only one solution, depends on kind of the Reynolds equation comes out from the problem, we can use different solutions. In previous lecture, we started with the finite difference method, indicating that hole bearing surface can be divided in number of nodes, and using Taylor series we can estimate temperature, or we can estimate pressure, not temperature, pressure profile over the bearing surface. We consider only the steady state Reynolds equation, where the time dependent term was neglected. The dH by dt is negligible for a steady state Reynolds equation, and we considered wave action, assuming the surface is rigid, there will not be any pressure generation due to variation in surface velocity. Surfaces are rigid, u is constant, is not a function of any space variable. This was a figure which we showed that two surfaces, and this was a grid which we showed to be used to estimate pressure P I j, pressure at any I and j node. This expression was used to indicate is related to Taylor series, and Taylor series was expressed right here that f function of x plus delta x and function f as a function of x minus delta x. Taylor series gives expression. When we subtract equation 2 from the equation 1, we get this expression, and this gives an approximate value of first variation or first derivative of f with respect to x. That was utilized to approximate pressure gradient, first order pressure gradient and second order pressure gradient, and get overall expression, something like that. For second order, P I plus 1 j minus 2 P I j plus P I minus 1 j. For the gradient in z direction, we have to write I j plus 1, P I j will remain same, while in case of z variation or variation with respect to z, we write I comma j minus 1. Substituting this value, and we can rearrange equation some thing like this: P I j, the pressure at any node in x direction and y direction where the cross section comes. We can write in terms of 4 pressures: P I j plus 1, P I j minus 1, P I plus 1 j, P I minus 1 j, and a constant term at that node, that is E I j. Other multiplication factors with all these pressure terms will remain constant at any one node, it will not change. However, the pressure will continuously change as per the iterations. It may increase if we are using the initial pressure as a 0 pressure, as a gauge pressure is 0 pressure, or the pressure is atmospheric pressure. Then we will slowly get more and more pressure at the node, and finally it will reach to a one saturation limit, and that saturation limit what we name as a convergence limit. That was indicated in a previous lecture and repeated over here. We are saying that at any point or at any iteration, maybe say iteration number k plus 1, we take values from a previous iteration, that P 1 2 from previous iteration, However, P10 will be known to us, that means we can take from the present iteration, while P21 from previous iteration, P01 again will be known to us, then it will be at the present iteration, while all other constant for the nodes will remain same, will not change with any iteration, it will be just repeated. And we can use a boundary condition as initial condition, not boundary condition, initial condition Pij is 0 at all nodes. Then this is a convergence criteria we have been we are using. We say that at any iteration k, whatever the summation of pressures or non-dimensional pressures for all the nodes, we say that when node varies from in x direction 1 to n, while in j direction in z direction from j 1 to m, and we are saying that this is not case sensitive, it can be capital N or small n, will be remain same. It will be subtracted from previous iteration, and overall will be absolute value. We are not talking about the negative value, we overall it will be the absolute value divided by absolute value of summation at the kth iteration. If we are getting this value is smaller and smaller, that means saturation is coming closer and closer, that is indicative, and that indicate with a number epsilon. Epsilon can be 0.01, can be 0.005, can be 0.001, depend on a solution accuracy required, solution accuracy. We took a example, we said that maybe assume the number of nodes in x direction are 25, number of nodes in z direction 25, and it requires roughly 30 iterations to reach to this solution accuracy. In that situation, we will be requiring number of steps of 25 into 25 into 30, that will be 18,750. However, if we take approximation, reason being that the dimension is very large in x direction compared to z direction, in that situation what will happen, the second term will be dominating. It is more like an 99% higher domination, obviously 99 times higher, not 99%, is 99 times higher. Then this term can be neglected for the to reduce the number of steps. And if we neglect this term, we require only terms in our number of nodes in z direction. We do not require any node in I direction as it is, independent node, and due to this what will happen, number of iterations will reduce. You are saying iterations may turn out to be only 15 instead of 30 to for a final solution. If we do that, which is 25 into 15 is turning out to be 375, means we are going to get benefit of the 50 times when we are using some logic. We say this second term is very much dominated compared to first term. First term can be neglected and second term only can be considered. That will give better results to us, not better results, faster results to us. Then we say that we will be covering this example in present lecture. So, we are starting. Here the pad dimension is mentioned that 10 into 100 mm, 10 mm is in x direction and 100 mm in z direction. So, this is x direction, this is a top view of this front view, and we are able to see this plate. That is z direction is having 100 mm, that is much larger compared to x over here. Then in addition to these two dimensions, we have a leading dimension film thickness, leading film thickness dimension and trailing film thickness dimension. What is the meaning of that? Film thickness at the entrance is known and film thickness at the exit is known. Indirectly we know the inclination. Once we know these dimensions, we know we will be able to figure out what will be film thickness at any cross section, at any value of x what will be the film thickness. Velocity or tangential velocity is provided in question, and viscosity of lubricant is also provided in this expression. So, what is required now to find out the pressure distribution, how pressure will distribute on this surface? Using this dimension, we say x by z, x is 10 mm, z is 100 mm. So, it will turn out to be 0.1. We use this 0.1 over here that is x by x square by z square will turn out to be 0.01, and this term can be neglected compared to 1 unit over here. 1 versus 0.01, naturally this is negligible, we can neglect it and we can use only this term. We know the clearance, it can be an average value of overall film thickness. So, 40 micron and 20 micron film thickness, and then we can find C. The C is 30 micron over here. So, C is known to us, capital X is known to us. What do we need? H bar. To find out the H bar, we need a film thickness expression, and that film thickness expression can be given easily. We say that the film thickness is decreasing towards the x direction. As the value of x is increasing, film thickness is decreasing. That can be represented with a simple expression, which is the H is H maximum minus H max minus H minimum divided by capital X. Capital X is the dimension in x direction, which in the present case is a 10 mm. So, here the value is already known, the 40 micron, minimum value of the film thickness is 20 micron. So, 40 micron minus 20 micron will be known to us as 20 micron. 20 micron divided by 10 mm, right. So, if we give in terms of meter, it turn out to be value 20 micron divided by 10,000 micron, ratio will be known. However, we know very well that we require x bar, we are doing a non-dimensional number, and x bar is simply x divided by capital X. So, that is why it is written clearly over here, x divided by capital X is x bar, and this 20 micron can be represented in terms of mm, that will turn out to be 0.02, and this 40 micron will turn out to be 0.04. Now, we can non-dimensionalize this film thickness using capital C value, that is in our case is 30 micron or 0.03. So, H bar in our case turn out to be 0.04 divided by 0.04 minus 0.02 x bar divided by 0.03. We can say simply it will be 4 divided by 3 minus 2 divided by 3. 2 can be taken common and 3 can be taken common. So, it will turn out to be 2 by 3, in bracket it will turn out to be 2 minus x bar. If I differentiate it, if I differentiate h bar with respect to x, this will turn out to be 0 minus 1, and we know the outside bracket is 2 by 3. So, this derivation of h with respect to x bar will turn out to be minus 2 by 3. Once I know this expression, I know what is the value of the source term, I can directly substitute this equation and carry forward either integration or numerical analysis of finite difference method. First, we will consider finite difference method. So, we know this term, and we know how to represent this pressure term, this derivation of the pressure term in terms of finite difference equation, that was learned in the last lecture, that will turn out to be h cube, h bar cube, I plus half naught p I plus 1. Similarly, h cube h bar cube I minus 0.5 and p I minus 1. This will be a summation of the film thickness I plus 0.5, I minus 0.5, or with the film thickness at this node, h cube of that and h cube of this at that node. Now, h is will be known to us. We can divide the overall value of x, capital X, in 10 division or 11 division. So, we will be knowing what will be the value at each node. That's because we will be knowing what will be the x bar. X bar will vary from 0 to 1. If I divide in 11 or 10 division, which is 11 number of nodes, then I can say x bar is x0, then 0.1, then 0.2, 0.3, 0.4, 0.5, 0.6 to 1. And that when we substitute those values, I can figure out what will be h high, h 1 in this case, h bar 1 will be 0, h bar 2 will be based on the point 1 of value of x. So, we can calculate on that, and expression can be written something like this. We can rearrange, or as I mentioned that we are taking in step size as a 0.1. This is non-dimensional number, vary from 0 to 1. So, we are taking a step of 0.1. If that is the case, we can directly substitute this 0.1, it will be 0.01 after squaring it, and that expression will be modified in form like this. Our right hand side will be 0.00002, and this is these are the values for x bar. On x bar at the initial node number 1 subbase is 0, node number 2 0.1, node number 3 0.3, node number 2 is 0.1, node number 3 0.2, node number 4 0.3, and node number 11 it will be 1.0. Now, these expressions are the film thickness expressions. The film thickness at that node, that means when we substitute value of x bar, what we get is something like a 1.33. Again, this is a non-dimensional number. This film thickness will continuously decrease because of the convergence. There is a taper angle, or there is a taper surface, or there is an inclination. That is why this film thickness will be maximum at the entrance and the minimum at the exit, which is shown in this case. Now, we need the film thickness of the half step, and the half step we can find out what will be the h I minus, initially it will be h I minus 0.5. So, that is turning out to be like something like this. We are talking about when h bar is equal to 1, what will be the film thickness at step 0.5 towards negative x. In that case, it turning out to be 1.3. However, the positive side, step 1 step ahead, it turned out to be 1.23. And this is what we can arrange value of h step ahead of that. Oh, sorry, in this case it will be negative side. So, it will be h I minus 0.5, it will be h I plus 0.5, and this is a cube. This is a cube of h I minus 0.5 cube of that means 2.2 is a cube of 1.3. Similarly, 1.88 is a cube of 1.23, and slowly we can move ahead. And the one good point is that whatever the film thickness is moving ahead, and what will be the node value is 1.23 is the same as we have calculated in previous step. 1.17 is same as a 1.17 earlier. So, similarly 0.77 and 0.77 is same. That is obvious. Whatever the way we are increasing the value of I by 1. So, wherever at any point we are getting I minus 0.05, we add plus 1 over here, that will turn out to be I plus 0.5. So, that is way we calculate, and now these values will not change, that will remain same for iteration to iterations. These values are not going to change. That is why it is always preferable to evaluate this value, keep away from iterative loop. That is why we do not require too many calculations. Once these values are stored, and these values should be repeated again and again in iterative loop. That iteration loop will come from the pressure, and expression is something like this. The Pi at any iteration can be given something like this: I plus 1, I minus 1, and I minus 1 will be known to me or known to us. So, we can use advanced iterations. This will be the past iteration, or we say that if I use a Pi k plus 1 iteration number, this will value will come from Pi p k iteration, or Pi plus 1 will come from the kth iteration, while Pi minus 1 will come from the present iteration, because the one value is already been calculated. And this is what we have already these values, this h value, this summation value. What is only going to vary? Pi plus 1, Pi minus 1, and from one iteration to another iteration, As I mentioned earlier, when we do not know initially any value of P, we write the value as a 0, and that is indicated here the 0th iteration. 0th iteration we are using P all the pressure value as a 0 0 0. Then we comes to the first iteration, and another thing is that we are using 0 value of pressure at the entrance and the exit. Those surfaces or those interfaces are open to environment. Pressure will be 0 at those interfaces. So, pressure at the initial value when x bar is equal to 0, pressure will be 0. Similarly, pressure at the value of x bar equal to 1 will be 0. Now, remaining pressures will be evaluated initially based on the term constant term value in this case. That is a constant term over here 0.000002. That is going to decide what will be the pressure value at any point. Of course, after dividing these are the finite numbers, we will be getting some variation in the value, and that is coming over here. Now, second value of pressure is going to get influenced with the first pressure value. That is what we are saying. If I write a P I2, P I1 is already known to me, and that this to evaluate P I2 I already have this value. So, sequentially we go ahead and we get the value, and we are able to see the pressure value is continuously increasing. There is already one source term plus increase in the pressure term. Compared to 0, it will be higher value. So, that is why the pressure value is increasing. Is increasing to a maximum up to the node 10 number node. Of course, 11 number node is a boundary value, and we have already specified that the pressure value will be 0 there. That will not change with any iteration, it will remain same. Coming to the second iteration, what we are getting some change in results. Increase in the value, instead of 4.9 we are getting 7.6, that is obvious. Here the P I is getting influenced with the P I plus 1 of previous step, that means it is getting influenced with this term. If we are calculating this P I, even though P I minus 1 is a 0, but here the P I plus 1 is already present to us, that is getting influence. That means the pressure value will increase at the second iteration, and this trend will continue. The interesting thing what we can observe here, earlier the pressure was maximum at the one node lesser than what we say the boundary node. However, in this case you can see the maximum value of pressure is happening at the node number 9 itself. Here the pressure was maximum at the 10 number node, here the pressure maximum is a 9 number node, and this is a what boundary condition is affecting. Boundary condition is 0 here, 0 here, it is affecting the results, and that is required also, because we know the pressure profile in this kind of tribal surface will be parabolic. Otherwise, it will not turn out to be parabolic, it will turn out to be some linear profile at the exit. And we can use this iteration loop. Say we keep adding finding the pressure summation that is happening over here. After iteration number first, we are evaluating a summation of all the pressures, which is turning out to be 1.1 into 10 s to minus 4. After that, we are again finding the pressure summation at the iteration number 2. Here it is more than earlier one, because all the pressures are increasing, but interesting thing is that we need to find out what is the difference. What is the difference between the 2.0 10 s to minus 4 minus 1.1 10 s to minus 4, and it should be divided by this 2.0 10 s to minus 4. So, this iteration loop or this convergence criteria need to be satisfied. When we do this kind of convergence criteria, we write instead of this term we write 2.0 10 s to minus 4, instead of writing this term we write 1.1 10 s to minus 4, and substituting value of this, that is a 2.0 10 s to minus 4. What we get overall is a ratio that is coming around 0.46. That means there is a 46% increase after iteration number 1. We continue it. Iteration number 3, as I mentioned, the first node and last node will be at the 0 value. These are the boundary condition, we are not varying it, and remaining other terms are increasing, like instead of 7.6, now pressure at the node number 2 has reached to the 1.0 10 s to minus 5, and these all are non-dimensional numbers. It is slowly increasing, and we are able to see the same trend maximum pressure occurs at the node number 9 instead of node number 10. So, pressure maximum pressure is 5.3, and summation also we can see earlier summation was 2.0 10 to minus 4, while here the summation is increased because of increase in value of the pressure 2.9 and 10 to minus 4. However, we are able to see even the pressure value of summation is increasing, but the difference is decreasing. Earlier this ratio was 0.46, now we are getting 0.3. That means, earlier the pressure variation was 46%, now pressure variation is 30%. That means, we are going towards a convergence side. That indicates with every iteration this convergence this value is decreasing. That indicates clearly that we are moving in the right direction, solution is stable, and we are going to get solution maybe after a number of iteration. That depends which kind of a scheme we are using. That this is after additional iteration, we can say that after this iteration this epsilon value is turning out to be 0.22, which is better than 3.0. That is why we can we say we prefer this convergence, and after doing a number of iterations, maybe say we can count maybe say 13-14 iterations, what we are getting this convergence value as a 0.05. That means, this is a 5%. We started the first iteration, it was 46%, and after 10-12 iteration it has reached to the 5%. That means, improvement is significant. We continue it if we have a time and we understood how the pressure profile is changing. Maximum pressure profile, maximum value of pressure is come here somewhere here. It is not even is a node 11, node 10, node 9, and is a node 8. It has moved to the node 8. Earlier it was in the node 9, all the cases 6.6 compared to 5.9, 7.7, 8.8, 9.7, 1.1, 1.1, 1.2, 1.3, 1.3, and here finally in this iteration it has reached to the 1.5 in the that means, it's shifting towards entrance side, of course, away from the midpoint, away from the slightly away from midpoint and away from the exit point, which is coming somewhere in between. And this is a pressure profile on how we can see how the improvement is happening. As we can see, the series 1 is iteration number 1. Initial iteration is the pressure 0. This is what we are showing. We have selected the 11 number nodes. So, node number 1, what is the pressure? Will be 0 always. That is a boundary condition. Node number 11, again pressure will be 0, because that is a boundary condition. In between, pressure is continuously varying. Initially, it was maybe say maximum value was a 10 number node. Then slowly it moved to the 9 number node, and is finally moved to the 8 number node. You can see there is a parabolic distribution, and if I take this as a midpoint, it is away from the midpoint and away from the maybe say exit point, and is coming somewhere in between midpoint and exit point. Pressure is continuously increasing with iteration. That is clear, and when we use some additional technique like over relaxation technique and all, then there is a possibility of sudden change in pressure variation. While however, if you are not using any relaxation technique, then it will take slightly more time, convergence time, but there will be a definite profile, there will be continuous improvement. Even the improvement may be slight, but there will be continuous improvement. So, this gives an indication on the how iterative loop iterative cycle works for the tribo surface when you are using the finite difference method, and we have taken approximation in this case because of the dimensional dimensions were large in x direction compared to dimension in z direction, and we say that with this kind of loop there will not be much problem. With this assumption there will not be much problem, because x by z square was in this case dimension in x direction was a lesser. So, it was a negligible effect, and that is why we consider only pressure variation in x direction. Right. Now, whatever we have done in this case is a non-dimensional number, but finally at the design stage we require dimensional numbers. For solution purposes, for the initial get a feeling of which term is more dominating, we have non-dimensionalized it, but coming to the final, when we substitute and we want to get the results in a dimensional numbers, and that is possible using this relation. We use this for the non-dimensionalization of the pressure. This is the clearance, this is the viscosity, velocity, and the maximum value in x direction. When we substitute this, we know the viscosity is a 10 millipascal second, velocity is a 20 meter per second, and clearance is 30 micron, and in meters it will turn out to be 30.03 divided by 1000, that is the cube of that. This is the 10 mm at capital X, the 10 mm. So, 10 divided by 1000, we make a value, and we can find the pressure profile at the iteration number 20. What will be pressure profile? Of course, in actual case pressure will continuously increase, and it will reach to the final one saturation limit, and that is after substituting these values, what we are finding the pressure somewhere 25 is a maximum value over here. After number of iterations, iteration maybe say 20th iteration, we are able to get this value as a roughly 25 bar, or it is a 25 bar, in this case of that 25 Newton meter peters is a Newton per meter square. Now, we can solve this equation using some sort of integration technique that can reduce the number of iterations. That is why I am repeating this example. We said again we are using the same dimensions 10 into 100 mm, that means the dimension in the x direction is negligible compared to dimension in z direction. Relative velocity is same, and maximum film thickness and minimum film thickness has been kept same, but we need a pressure distribution, and if we are able to solve it analytically using some sort of integration technique, then we can really save iterative loop, and we can find convergence without going through convergence loop. To do that, again we can take a few steps, there will be some repetition of steps. So, in this case f x by z is a 0.1, that means this term is negligible, and we are getting only this term. Further, we know the what will be the clearance, that is turning out to be 30 micron, and we can express h in terms of x, which was done in earlier case also. H is in terms of x, but it is in mm. We need a non-dimensional number, and non-dimensional number is turning out to be 2 by 3 2 minus x bar. While the gradient is known to us now after differentiation, because there is x term here, and we can find that is a gradient is a negative 2 by 3. We can substitute this. Now, what we have? We have terms in terms of this expression in terms of x bar. We can integrate twice and get the value. So, first integration gives one integration constant, as nothing is here, it is a constant term, it will turn out to be 0.002 into x bar plus C 1, that is integration constant, and we need to determine it. However, we do not if we do not know anything which is not well defined, what we can take approximation, we know the pressure will be maximum somewhere, and pressure some location maximum, some location pressure will be maximum. We can use this as a gradient based approach. We say wherever the pressure will be maximum, this gradient will be 0. So, we need to find estimate x will be having some constant value where the pressure will be maximum. So, I can say pressure will be maximum at some location x bar p max. Using that condition, assuming this gradient is equal to 0 at x bar p max, which is a we have given as a symbol or the nomenclature, we are given the nomenclature to the location of maximum pressure, that gives a value of C 1 in terms of this location, but it helps us, we can know this is the constant value, it can be further integrated without much problem, right. And when you substitute this value, we get this expression. This need to be integrated once more to find out the pressure value, because in this expression is giving us only the pressure gradient, it is not giving us a pressure value. We require a pressure distribution, we do not require a pressure gradient. To do that, and we require expression of h, that is already we determined, that is a 2 by 3 2 minus x bar. Substitute this, rearrange equation, we know is a h bar cube. So, cube of 2 will turn out to be 8, cube of 3 will turn out to be 27, and this will be 2 minus x bar cube. We can rearrange this equation something like this and then integrate it. You see x bar p max minus x bar, integrate with respect to x, and this is also depending term, this is a function of x bar. So, this term has a function of x bar, this term has a function of x bar, and remaining will be constant, will be out. So, out of the integration bracket, it is turning out to be this integration, this constant is a 0.0067, and whatever we get from this expression, that is going to decide what will be the pressure. We can do some manipulation. We can say let us put subtraction -2 and addition 2. That means -2 plus 2 will make it 0. We are not losing anything, but however, we are able to make one bracket, it will turn out to be 2 minus x, separate expression, and this will turn out to be constant. So, we can get a 2 integration terms something like this. This is a x bar p max minus 2 divided by 2 minus x bar, and the whole bracket is a power 3, while in this case 2 minus x is already there. So, that 2 minus x will be cancelled out, and remaining term will be 2 minus x bar to power 2. Now, I can integrate easily this, I can integrate easily this, and once we integrate, we can use some sort of integration constant that can be resulted, that can be evaluated based on the boundary condition which we know. So, if we do integration for the first term, this is the same, this is a constant term x bar p max minus 2, while the integration of this will be a 2 minus x bar power 2. This is a minus 2 will be here, and this is the negative x bar. So, it will be negative. So, minus 2 and minus 1. Coming to the integration of second term, this is 2 minus x, this will give power minus 1, and x is also negative. So, it will be minus 1 plus integration constant, which we need to determine later. Now, I can rearrange this equation, and we can say this is a overall equation in terms of x bar, or this equation express pressure in terms of x bar. So, rearrangement can be done. However, we have one value x bar p max which is not known to us. So, what we can do? We can say we can find out by some boundary condition. Similarly, we have another constant C2 which is also not known to us. So, that also can be determined by pressure boundary condition. That means, we require 2 pressure boundary conditions, and we know at the entrance and exit pressure will be 0. So, we have 2 boundary condition, we require 2 boundary condition. So, there is a definite solution for that. So, we write first condition is a p bar is 0 at x bar 0, that is going to give that this x bar is 0, x bar is 0, substitute pressure is 0, rearrange the C2 constant, or constant C2 will be in negative, x p max, that is the location of maximum pressure, minus 1 divided by 2. Now, we have we can substitute this value in this expression to simplify the expression, and but we get a result something like this. Now, we can use a second boundary condition, that is a pressure 0 at x bar equal to 1, and that is going to give us location of maximum pressure. When we substitute it, it turned out to be x bar p max is a 5/3, that is a non-dimensional term, and this is a value given over here. Now, we can substitute, we get a result something like this, and rearrange or directly we can use to find out the results. If we try to use 11 value, we say that let us take x bar as 0, x bar as 0.1, x bar as a 0.2, 0.3, 0.4, 0.5, up to 11 node, the way we have done for the numerical analysis or finite difference analysis, then we can compare the results. When we do that, we get a pressure profile something like this. This is simple, use just substitute value, get the pressure value, no iteration. In one iteration we are getting solutions. So, this is maximum value is coming somewhere here 0.7, that means the node number 8, node number 11, node number 10, node number 9, node number 8, and this is a what we same value similar expression, or say that same location we got a maximum pressure earlier, right, and that is a non-dimensional number and slightly more than 0.00025, which we already evaluated. This is a series, we say iterations are given, we are comparing with the previous results, that is something like maximum pressure again is happening at somewhere here, node number 8, this is also node number 8, only the difference in the value is happening because of the lesser number of iterations have been done, and then finite difference method we require more iteration to reach to this level. That is possible. We can do more number of iteration to reach this value. However, this does not require any iteration. In one iteration, obviously, then one calculation, it is straightforward, gives the results. So, efforts required to find out this curve is much lesser than efforts required to use this finite difference method, and we have more reliable results here. It does not require any time step as such. We can reduce, we can increase number of steps to the find out more smoother curve compared to this curve. So, in short, this is a better method. If it is possible to integrate, we should integrate it, we should get the results without going through the numerical calculations. However, there are some drawbacks also in this. We say we know pressure profile only in x direction, we do not know pressure profile in z direction. We need to find out, either we substitute some expression to find out the pressure profile in z direction. However, before coming to that, let us take another example, just other dimension. We say let us in this case we assume that dimension in x direction are too large compared to z direction. So, in this case we are just taking separate thing. We say let us take a thrust bearing pad or thrust pad is 100 mm by 10 mm. That means, dimension in x direction is 100 mm, while dimension in a z direction is 10 mm. So, we have x by z is a 10 in this situation. When x by z is 10 mm, sorry 10 times, then this second term is going to get dominated. In earlier case, this value was 0.1, while in the present case this value is 10. In earlier case, we consider this term as a dominating term, we neglecting second term, while in present case we are going to consider second term, we are going to neglect first term. That is advisable to some extent, because it is going to give good results to us. Now, this term is neglected, remaining two terms will be there, left hand side pressure term, right hand side waste term. We know right hand side term can be easily calculated based on the clearance and finding the expression h, that is given over here, expression h in terms of h max and h min and variable x. When we do this, and we can find out also gradient, that is we have done this 2 times earlier. So, I am just going slightly faster here. We are saying that this is a minus 2 by 3. Substitute this. What is the advantage in this? H is depending on the x, it does not depend on the z. So, integration in this case will be much simpler compared to the previous example, where the integration was slightly difficult. Maybe we really require integration, it was not coming without constants. It coming with constant, which required some additional calculation, while in the present case integration is much faster. We can simply take out h cube, rearrange this equation in this term, and this is a constant. Integrate 2 times, after 2 times integration what we get here, z bar square divided by 2 plus integration constant. As the integration constant first, we can multiply with the z bar and then integration constant 2. So, we have 2 integration constants and we know we have a 2 pressure condition P 0. So, at z is equal to 0, P 0 at z is equal to 1. We already have this pressure condition, we can find out, we can substitute these values and get the results. Right. So, results are turning out to be something like this. When we write a z bar 0, z bar 0, pressure also 0, naturally C 2 will be 0, that is given over here. Second condition, when z bar is equal to 1 and 1 over here. So, this is a simple expression and C 1 turn out to be 0.00001 divided by h bar cube. You substitute this value, we get this expression, and of course, we know this is a parabolic plus some addition from z is also accounted over here. This is the pressure variation in terms of z variable. We assume that pressure variation in x direction that not be that much important to us, even the maximum value of pressure in both the cases will be same. However, in this case we are getting advantage, we have to use only one variable, that is the z bar, and again the way in previous example we considered the values in terms of x bar, take the values x bar equal to 0, 0.1, 0.2, 0.3, 0.4, and based on that we can do this calculation of the pressure, or we can find out the pressure distribution. Same thing can be done in this case also. Now, we have z bar values which is known, h bar is already known, and we can find out pressure distribution. However, another important thing in the present example is that we have x bar value also. H is a term is expressed in terms of x. So, we have added advantage compared to previous example, added advantage in terms of like we have x bar value as well as we have a z bar value. So, it gives a two dimensional pressure distribution, may not be 100% correct, but it is going to give us dimensional variation in the two direction, in x direction as well as the z direction, while in earlier case we found only the one profile that was varying in only in x direction. We assume the pressure variation in z direction is not important, and we have not used any pressure boundary condition related to z in that situation. So, if we use this and maybe say we better arrangement, we rearrange this equation, we take out this constant and we take out the h bar value is expressed in terms of z bar and 1 minus z bar. This also gives a confirmation to us whether we have calculated a pressure profile right way or wrong way. In this case, when we are taking using this expression, this clearly says whenever the z bar is equal to 0, pressure will be 0. Similarly, whenever there is z bar is equal to 1, pressure will be 0. So, this is confirming what we have done, that is a proper, it is not we are not made any mistake in evaluating this expression. Now, already film thickness is known, that is in terms of x bar, and I mentioned clearly that this is better pressure profile compared to previous one, because this is also expressing pressure in terms of x bar. It is not only the z bar, it is also expressing in terms of z bar in terms of x bar. So, it is giving a two dimensional profile. If you remember previous slides, and we express the pressure only in x bar term, there is no z bar at all in this. So, this is giving only the one dimensional pressure variation, it is not giving a two dimensional pressure variation. Compared to that, this approximation is a better approximation. Only thing is that dimensions were very different. In first example, our previous example, we consider x dimension maybe much lesser compared to z dimension, while in present example we are considering x dimension are much larger compared to z direction. So, we get some pressure profile something like this. Now, this is a nice picture as such. Now, we can see z direction and sorry x direction as well as z direction, we are consider same number of steps. calculating at the when a value of x bar is 0, 0.1, 0.2, 0.3, obviously number of nodes are 1, 2 to 11. Similarly, in z direction also number of nodes are 11, we are pointing that, and based on that we are evaluating the pressure profile. So, what is the difference in this? Even though it is a parabolic pressure profile at the every cross section, but there is an increase in a pressure in z direction also. It is giving good results one way, but bad result another way. We know pressure will be 0 whenever there is a value of x is equal to 0. The 0 value, it will be 0 irrespective of value of z. When x bar is equal to 0, pressure should be equal to 0. It should not vary with z bar. That is not indicated. We can see there is a pressure profile over here, which is not right. Similarly, pressure profile is not right in this case. So, that is a drawback, but it is a better than first approximation. That is why we require some sort of hybridization. We are getting some good results from one side, and we are getting some good results from other approximation. It will be always advisable to hybridize these two approaches and get an overall good solution from these solutions. So, we will continue that kind of hybridization in next lecture, which will be basically hybridization of when we are neglecting one term and we are getting pressure profile from that, and neglecting second term and getting pressure profile for that from that, and when we are getting two pressure profiles, both have merits, and when we combine in such a manner, whatever the demerits these individual pressure profile have, those should be eliminated one way or another way. So, we will discuss that kind of hybrid approach in our next lecture. Thanks for your attention. Thank you.